Every spring, tornadoes devastate communities, ripping homes and families apart.
Everything's such a tangled mess, you can't tell what's what.
I've never seen devastation like this.
But last year, 2011, stands out as one of the worst years ever.
I remember the things falling on me, and I was afraid something big was going to crush me to death.
Over 550 lives are lost in a multi-billion-dollar trail of destruction.
Houses are gone, people are thrown, injured. I know we're going to have casualties. It's massive.
What can be done to prevent such disasters in the future?
Our house isn't even here anymore. We have to figure out a better warning system.
But a better warning system requires a better understanding of tornadoes, still among nature's greatest mysteries.
There's an urgency to try to crack the code. So we have to keep going and get data as often as we can.
And that data could lead to better prediction and save lives.
To see so far in the distance and there be nothing, like someone dropped a bomb.
NOVA follows the scientific investigation into tornado season 2011.
Something you don't ever want to have to live through ever again.
We trace the events of one of the deadliest tornado seasons ever and follow the race to prevent future disasters.
There's more supercells dotted down the line all the way through North Texas.
By warning people earlier in life or death situations.
They love the weather here. Well, you know, if they don't pay attention, they die.
On the anniversary of one of the worst tornado seasons ever, can we solve the riddle of deadliest tornadoes? Right now on NOVA.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science.
Discovering new knowledge. HHMI.
And the Corporation for Public Broadcasting. And by PBS viewers like you. Thank you.
In a terrifying onslaught, over 1,600 tornadoes strike the United States. It's 2011, the worst tornado season since 1925, with 550 deaths. The most destructive incident is a single tornado that touches down on May 22nd. Joplin, Missouri, 5:30 p.m. It's just another Sunday evening, and then...
all hell broke loose above us.
A massive tornado drops out of the black sky.
It's cover on the ground right here. Like, get the sirens going, get the sirens going, I'm telling you.
The deadliest single tornado in the U.S. for 6 decades rips through the south side of Joplin.
There it is. Oh gosh, that is a monster tornado.
While people run for shelter, their homes are hit head-on.
It felt like the whole earth was shaking, and you could just feel something that just wanted to grab you.
This powerful tornado brings death in its wake. People fear for their lives.
You could feel yourselves just kind of rise up, like my 15-year-old was asking me, Mom, are we going to die? Are we going to die? And I'm telling her, no, honey, we're not going to die. We're okay. We're safe. And then in the back of my mind thinking, yeah, probably.
Spinning at over 200 miles an hour, the mile-wide Joplin tornado devours everything in its path.
At that point in time, I was just scared, thinking we wasn't going to make it. Like a train was coming.
And the whole foundation, the house, everything was shaking.
The tornado kills more than 160 people and injures hundreds more, destroying thousands of homes, leaving whole neighborhoods in shock.
I don't think it dawned on us what had happened until we looked at the neighborhood. And it was like, there was no comprehension whatsoever.
People returned to find their homes gone, knowing what would have happened had they remained.
We wouldn't be alive. I mean, as you can see, we would have been caught in our kitchen, and our house isn't even here anymore. So whoever has the power, if it's even able, we have to figure out a better warning system.
Tornado warnings are often too late to save lives, but a better warning system poses challenges for scientists.
Joplin, basically we saw this swath of severe weather potentially, but it would be very hard to say well in advance that this part of Missouri was going to be at risk.
Meteorologist Greg Carbon coordinates warnings at the Storm Prediction Center in Norman, Oklahoma.
I've been in meteorology for almost 25 years, forecasting, and it is mind-boggling to sit back for a moment and think about the advances that have been made in just that short period of time. But the ability to forecast a tornado event prior to an actual thunderstorm forming is an ability we still don't have.
Although almost every tornado begins with a thunderstorm, not all thunderstorms produce tornadoes. The difficulty is predicting which thunderstorms will be most dangerous.
That's a double-edged sword in meteorology. You don't want to incite panic and you know, talk doomsday scenario, but then again, you don't want to be so careful and quiet that people don't get the word.
But it's not easy. Thunderstorms can be predicted days in advance and detected within hours of forming by satellites, weather balloons, and radar. But tornadoes are born in minutes. The most effective prediction tool today is Doppler radar. It works by firing microwave pulses at raindrops to reveal their distance, speed, and direction. This distinctive hook shape often indicates that a thunderstorm has started to rotate and could spawn a tornado. It kickstarts the whole process of alerting communities at risk. When a tornado warning is issued, the amount of time that elapses between the warning and when the tornado strikes, if it does, is called lead time.
By lead time, we mean that the tornado will hit your place in X minutes.
The amount of lead time can be crucial.
Certainly, if you have an hour warning, you can avoid a traffic jam, you can get out, you can drive away and be safe.
But the average lead time that Doppler gives is only 13 minutes. And it's not fail-safe. To avoid false alarms, people on the ground are needed to report what's happening locally.
It's coming up north. There's debris. There it is. Tornado's coming in the city.
Gary England was the first TV meteorologist to use Doppler radar for tornado warning in 1981. But he still counts on tornado chasers.
You can have the fanciest radar in the world and you don't really know for sure. It's just a piece of electronic equipment. You need the eyes on it. You have to have that person in the field that says, yes, I see a tornado. No, I don't see a tornado.
But once a tornado is on the ground, it may be too late to help people in its path.
We are trying to anticipate the formation of these, but really our challenge is to try to anticipate and forecast that development before it occurs.
So the race is on to improve lead time. But like the weather itself, tornadoes are complex and varied. Still, scientists are coming to grips with the nature of these violent storms.
A tornado is a rapidly rotating column of air.
It's in connection with both the ground and also the base of the thunderstorm.
Cold air descends with rain and hail and wraps around the circulation.
And if they concentrate that circulation in certain areas, you have a tornado.
This is a typical tornado, spawned from rotating winds in a thunderstorm called a supercell. Most tornadoes are small and local, with wind speeds less than 110 miles an hour. The most extreme tornadoes are 2 miles wide, with 300-mile-an-hour winds, and travel hundreds of miles.
We certainly know what a tornado is. However, the big mystery is trying to discover why a tornado forms. We don't understand why some thunderstorms produce tornadoes and others don't. Only a very small fraction of them, 10% or perhaps even fewer, storms go on to produce tornadoes.
So how can we get better at predicting which thunderstorms will produce tornadoes? At the University of Oklahoma in Norman, Howard Bluestein has been asking this question for decades. His research has been key to increasing lead time, but he is determined to go for more. So every year, he's out looking for tornadoes. Here in Tornado Alley, a wide swath of land between the Rocky and Appalachian Mountains. It's April 2011, the start of tornado season. Howie and his team are on the plains of Oklahoma, the heart of Tornado Alley, testing their new mobile Doppler radar. So far, all is quiet. But 100 miles away, in another part of Oklahoma,
I'm calling to report a tornado. It is on the ground just west of Stroud, Oklahoma.
a tornado touches down in Stroud, the first of many in this area.
Oh no. Oh no.
The average tornado lasts 2 to 3 minutes. Today, some of these tornadoes are going for 10 minutes and longer.
Whoa, that's violent. That's incredible.
Over several long hours, Alabama, Arkansas, Mississippi, Oklahoma, and North Carolina are all struck by tornadoes. It's typical this time of year in Tornado Alley. But why? It starts with cold winds coming in.
During the springtime, we have air coming in at high levels in the atmosphere. Comes in and it goes up and over the Rocky Mountains, and it subsides and it warms. And that makes southerly winds out over the central part of the United States. And those southerly winds bring in a relatively warm, moist air off the Gulf of Mexico and overspreads the plains area.
This creates huge thunderstorms. Then winds coming in from different directions produce spin.
The winds turn with height, and they become a lot stronger with height. So we have a source of rotation within the storm.
This is what tornado chasers record beginning on April 14th. Strong storms over a wide area starting to rotate. This one over Tushka, Oklahoma, becomes a tornado, killing 2 people. But that's just the beginning. Over 52 hours, 155 tornadoes touch down in 16 states. 38 people lose their lives from Texas to North Carolina. This is a shocking start to tornado season. Described as one of the largest single-system tornado outbreaks in U.S. history, scientists are asking, is it an isolated incident or part of a pattern?
We saw a number of these events. We saw around the 16th of the month a major tornado outbreak in North Carolina. The questions became, can we predict that this pattern will continue?
To answer that question, Greg compares the April 2011 outbreak to previous seasons.
Well, we actually have a system that will take a forecast and it will compare that forecast to historic weather events of the past. So there was a good analog for this event that had occurred in the past to the forecast pattern that was coming up in the days ahead.
When Greg examines his data, the result is not reassuring.
The match that came up was a Veterans Day event of November 2002. Nearly 40 fatalities associated with that event. Kind of an unusual time of year, not the spring, but actually the second, what we call the second season of activity.
Fall 2002 saw 76 tornadoes sweep through 17 states. Greg is concerned about the position of the jet stream, the river of air that circles the Earth high in the atmosphere, affecting the weather. It's shown here in blue.
This is the November jet stream pattern that was in place in the year 2002. And we can see the similarities with this event in 2011. Jet stream diving across the Rocky Mountains and driving intense thunderstorms across the southeast Tennessee Valley and Ohio Valley. I sent email out to the National Weather Service, publicly available through our website, talking about the fact that the upcoming event showed signs of similarity to the outbreak that we saw in November 2002.
There's cause for concern. Some meteorologists believe it could be even worse than the 2002 Veterans Day outbreak. A tantalizing clue lies off the coast of Peru. The Eastern Pacific, July 2010. Ocean buoys record unusually cold sea surface temperatures. This is called La Niña, and for centuries, Peruvian fishermen have been aware that it not only affects their fishing, but also the weather. Scientists can now measure the effect. Here's the way a La Niña looks on a satellite's thermal imaging camera, showing the cooler sea temperature off the coast of Peru in green. Scientists discovered that the huge expanse of cool La Niña water could affect the surrounding atmosphere and the jet stream, shifting severe weather into new areas and intensifying it in places like the southern United States.
We had a very strong La Niña in the wintertime that set up a strong jet stream that provided the wind speed energy that was necessary to generate thunderstorms. But we also then had very humid and moist air in the southeastern part of the United States that provided the fuel for these thunderstorms. And the combination of those two provided an environment that was more conducive to these large tornadic outbreaks than you might have in other years.
By spring 2011, the newly intensified jet stream was already contributing to rainfall and floods across the South, plus droughts and raging wildfires in Texas. Warning signs of historic weather extremes.
We were worried about it because when you have a La Niña, as our research has shown, there tends to be more family outbreaks of these tornadoes in the southeast United States.
In fact, one of the worst tornado events in history, the super outbreak of April 1974, also took place in a La Niña year. 148 twisters touched down in 13 states, from Mississippi all the way up to New York, killing 330 people and injuring thousands. But will the pattern hold in 2011?
It's crossing the interstate right where we were.
On April 25th, at 7:25 p.m., violent storms erupt in Vilonia, Arkansas, the start of 52 hours of deadly tornadoes.
Here comes the rain. Boom.
The worst day is the 27th of April, starting at 2:30 p.m.
A large, violent tornado that is down on the ground.
A powerful tornado touches down in Philadelphia, Mississippi, and kills 3 people. 30 minutes later, Hackleburg, Alabama is hit, killing 18 people. Then Cullman, Alabama, leaving 19 dead. 4:45 p.m., Tuscaloosa, Alabama. Classic anvil-shaped clouds form supercells, thunderstorms where rotation has begun, as Greg Carbon observes.
I came out into operations during the late afternoon. You were seeing incredibly well-formed supercells, the likes of which was truly stunning.
A distinctive hook echo, the radar signature of a fiercely rotating storm, heads toward Tuscaloosa.
With every one of those hook echoes, you had a violent tornado on the ground.
This is a large, violent tornado coming up on downtown Tuscaloosa. Be in a safe place right now.
A 1.5 mile wide tornado cuts through the heart of Tuscaloosa, leveling entire blocks and tossing trees and power poles around like toothpicks. Tornado scientist Chris Weiss recalls.
The storm that affected Tuscaloosa actually initiated back in Mississippi. Actually traveled for, I think, a good hour and a half, and then produced its tornado. It stayed on the ground all the way up into Birmingham. The storm itself actually lasted 7.5 hours because of the various dynamics with the storm, producing tornadoes along a good chunk of that length. You see regions all across northern Alabama, into northwestern Georgia, even up into western North Carolina. Tennessee was also affected. So a tremendous number of tornadoes for this outbreak.
The 52-hour onslaught produces 343 tornadoes, the most ever recorded in a single outbreak. Families in trailer homes and timber-framed houses lose everything.
Most of this is sentimental to me because it's my mother's and I've been had it for 40 years and I can't get any of it back. I can't get any of it back.
Even brick houses couldn't withstand the force of this tornado. Whole blocks are virtually flattened.
It is unreal. It looks like a third world country or a place that has been strategically hit by war.
In Oklahoma City, TV meteorologist Gary England follows the path of the storms on radar.
We watched them from here. We can look at the radars, and you can see the tornadoes developing, you know, massive supercell thunderstorms, big rotations inside. The rotation sometimes becomes the entire tornado, and that's what was happening down there, and it looked like a fleet of them. They were just coming across there.
Oklahoma is lucky to escape this time, but the impact is devastating. Although disaster investigator Tim Marshall sees it often, he is always shocked.
I have always been surprised by the power of tornadoes. I mean, after all it is air and water, so how dangerous could that be?
Investigators like Tim use a system called the EF scale to measure the strength of tornadoes by rating the damage they do.
Typically, every year we get 1,500 tornadoes in the U.S. EF0 is damage to tree limbs, some shingles off of a roof or so. And then EF1 is more substantial damage, like some roof decking.
An EF1 can be powerful enough to overturn a mobile home.
EF2, the roof is gone.
The aftermath of even an EF2 can look like a bomb exploded.
EF3 is basically the outer walls of the house are down and only the interior walls remain.
And EF3 releases the same amount of energy as 10 tons of TNT, like the tornado that hit Haleyville, Alabama on April 27th.
EF4 is basically all the walls are down with just a pile of debris left on the foundation.
Very little is left standing after an EF4 tornado. This EF4 hit Cullman, Alabama on April 27th.
And EF5 is complete sweeping clean of the foundation, of the house, of all the belongings, such that there's only a little perimeter left in the ground where the house once was.
And an EF5 is equivalent in damage to the atomic bomb dropped on Hiroshima On April 27th, an EF5 tornado strikes Smithville, Mississippi.
To have an EF5 go through a major metropolitan area is rare. I mean, less than 1% of all tornadoes get to be that strong and get to produce that kind of intense damage.
There are 4 EF5s on April 27th. The large Tuscaloosa tornado is rated an EF4.
We're alive, our neighbors are alive, and our son is alive, and so we're okay.
It killed 64 people. Many more could have died had it been an EF5. Overall, the April 2011 death toll hits 369. President Obama visits Tuscaloosa to support the shattered community.
I've never seen devastation like this. It is heartbreaking. Some residents here were lucky enough to escape alive, but have lost everything.
The death toll is a stark reminder of the need to increase lead time to get people to safety.
That is a tremendous circulation over in parts of North El Reno.
But it used to be worse.
It's a clear wedge tornado, Gary. About a quarter-mile wide wedge tornado.
As Gary England recalls.
You know, when I first came here in 1972, the lead time on how early could we get a tornado warning out was probably about -2 minutes. The warnings in those days were just absolutely terrible. Equipment wasn't too good. The radars were nice, but just nothing to go with, no computers. And I could only warn you because it blew someone else's house away down the street. That's how bad the warnings were.
Sit down.
This 1950s government information film on tornadoes illustrates how limited tornado warnings were.
I gotta keep watching the southwest side. It's where most of them come from.
You think it's likely?
No. The odds are way against it, even in weather like this.
Forecasters had to rely on ground observations and weather balloons to tell them if storms were coming. In the 1960s, satellites were launched to observe cloud formations and give readings of Earth's temperature. But when Doppler radar was introduced in 1973, scientists could clearly see the hook echo, signaling that rotation had begun. Powerful computers that could analyze vast amounts of data helped get the tornado lead time to today's 13-minute average. This has saved many lives, but could it be better? Most forecasters believe that a breakthrough will only come by unlocking more detail on exactly how a tornado forms. Howie Bluestein and his team intend to do just that. They've developed a new Doppler radar to carry on their truck. If they catch a tornado, it could give them enough data to create a computer model they can use to evaluate future storms.
What people are trying to do is to take weather data and put it into a numerical model, and then let the numerical model produce tornadic thunderstorms. So then you can issue a forecast and say, there's a 20% chance that in your neighborhood, 4 hours from now, you might get a tornadic thunderstorm.
The main question concerns rotation, as Chris Weiss explains in a tornado simulator at Texas Tech.
To get a tornado, we need that storm to acquire supercell attributes. That just means that the wind is coming from different directions and speeds with heights.
The supercell storm starts with air clashing and spinning, mostly in a horizontal direction. To turn into a tornado, it needs to go vertical.
We need to have an updraft, an area of very quickly moving air, pulling the air upwards very quickly. And what that does is it takes the spinning air and it stretches it in the vertical. So you can imagine that, say you had one of those Chinese finger trap toys and you pull on it on both ends, it constricts that axis of rotation, it makes it spin faster. That helps us explain most of how tornadoes form, though we don't have a good handle necessarily on the mechanisms that create that spin near the ground though. And that's where a lot of the research is focused at the moment.
So vertical spin is only part of the picture. What else can turn a rotating thunderstorm into a tornado? If scientists can work out other possible factors, like wind speed, temperature, and pressure, they may be able to, in effect, reverse engineer a tornado.
This is a supercell that's moving to the southeast. I cannot discern any rotation visually, but we need to keep an eye on that.
Out on the plains of Oklahoma in late April, Howie is hoping to get close to a tornado with his new mobile radar. Earlier models scanned the sky about every 2 minutes. This new radar does it every 2 seconds. It also scans in minute detail, capturing the actual size of raindrops, hail, and debris.
There's a funnel cloud due west of us. It doesn't appear to be very intense.
His new radar could significantly advance tornado science. But first, Howie needs a tornado.
There are also a cluster of 3 cells to our northwest, and they look fairly good on radar, not great. So we're just going to sit here and wait.
Although it's been a very active tornado season, today there are none on the horizon. But the team shouldn't have long to wait. Historically, May is even worse than April. 3 weeks into the month, it's eerily quiet.
We do know that May is usually the most active month for tornadoes. Fascinatingly, this particular year, right after the events of April 27th, these active storm track broke down. After a record April, as far as tornado events, we were headed for a record May as far as the fewest tornado events on record. And then Joplin.
On May 22nd, a large thunderstorm heads toward Joplin, Missouri.
Oh my gosh. Oh my gosh.
Suddenly, a lone and enormous EF5 tornado touches down. The tornado emerged from some unique weather conditions. As Tim Marshall explains.
The thunderstorm that produced the Joplin tornado began in Kansas.
Forming at 2:30 p.m.
Southeast winds came in from the surface, and up aloft there was southwesterly flow. And this action here produces a spin.
Then, higher than normal ground temperatures produce an updraft of hot winds.
And that updraft tilts that into the vertical and produces this counterclockwise rotation.
At 4:15 p.m., rain and hail begin to fall.
Cold air descends with rain and hail and wraps around the circulation. And as it crossed the state line between Kansas and Missouri, just west of Joplin, a tornado was born.
The tornado is spotted on the ground at 5:34 p.m.
It's a massive tornado, massive destruction.
Oh, these poor people.
I know, I know. Yeah, South Side of Joplin's gone. It is like an F4.
It's gone. It's gone. There's people in there.
I know. Come here.
People everywhere.
Hello? Hello? Oh, come here, sweetie. Come here, honey. Come here, sweetie. It's okay. Come here, baby. Come on, sweetie. Oh, come here, baby.
Everything's such a tangled mess, you can't tell what's what. It's really hard to think about all the hard work that's gone in here just being gone.
Tried to lift us off the ground, and then we'd settle, and then we'd lift, you know. And so it was over in, I don't know, I'm going to say 2 minutes.
With over 160 deaths, Joplin is ranked as the 7th deadliest tornado in U.S. history, the worst since 1947.
The Joplin situation, as far as I'm concerned, was a disaster waiting to happen. Not many tornadoes go through the suburbs there. They're not used to this.
Joplin hasn't been hit by a major tornado for decades, and development has placed more people in harm's way.
It's amazing that this window stayed intact, because had it not been intact, I'm sure that the debris would have been flying in on us.
It's a painful reminder that in a tornado-prone region, residents can never let down their guard.
I remember the things falling on me, and I was afraid
something big was going to crush me to death. I remember I remember laying there and feeling like pieces of wood hitting me, and how I didn't get some of this wood that has like the nails and stuff in it.
I know.
When I first drove up on the scene, it was just utter devastation. I first looked at the school, and my first thought was, when I was younger, about the Oklahoma City bombing. That's what it looked like from the outside.
Joplin High is ripped apart by thousands of pieces of glass, slicing through everything in their path. Timing saves the students' lives because the EF5 tornado struck on a Sunday. Tim Marshall flies into the immediate aftermath. His goal is to understand the tornado by studying the damage it left behind.
You know, it's hard to absorb all of this damage no matter how many times I see it. It's numbing in a way, because it's every one of those little blobs down there of debris was a house, and there was a family there.
From the air, Tim can see where the tornado started just outside of town and how its path rapidly widened.
This tornado track tells me in its intensity that there was no safe place really above ground. And it's sort of like a big saw blade shredding house after house.
On the ground, he studies the debris for any evidence the winds left behind.
I look for clues that indicate how strong the winds were. So that weighs many hundred pounds right there. The heavy weight of this concrete parking curb being moved like that tells us that the low-level winds were very strong.
The Joplin tornado is so powerful, it twists the local hospital 4 inches off its foundation. Most houses suffer much greater damage.
The tornado's only in contact with the house for a very short period of time. I mean, this all happens in 30 seconds to a minute. So the heavier your building, the better, and the more apt that you're able to survive it. If you're inside a car and you're close to a window, you can be sucked out of the vehicle by the differential pressure.
Even light materials on the loose can be deadly.
Now, a piece of cardboard's pretty flimsy, but if a piece of cardboard is traveling at 200 miles an hour, then it can go right on through things like this. It can go right on through the human body.
Tim wants to help people survive the worst that nature can throw at us.
Within the mangled mess left behind by tornadoes, that's Mother Nature's fingerprint to me. And I try to make sense out of it, putting back together the pieces and seeing where the fatal flaws are in building construction.
He's hoping this knowledge can be used to strengthen buildings to withstand tornadoes, a force of nature we can't avoid.
We can't stop tornadoes. We're going to have to live with tornadoes. 2011 has been absolutely a gangbuster of a year for me in terms of disasters. I've never looked at that many major disasters in one year.
And it's not over yet. It's late May, and Joplin is not the end of the vicious 2011 tornado season. More storms are heading for towns all over Oklahoma.
All the indications were that this was going to be a major tornado outbreak.
12:30 p.m., May 24th. Just 2 days after the Joplin tornado, Gary England goes live from Oklahoma City, forecasting trouble.
Moving right now is this particular way, so take immediate tornado precaution.
His forecast is based on National Weather Service alerts, his own Doppler radar, and tornado chasers phoning in from across the state.
Gary, this is going to be a large tornado now. It's about 1/4 mile to 1/2 mile wide.
40 years of experience have prepared him for days like this.
If you live from Chickasha on northeastward, take your tornado precaution. This is another giant tornado, preferably a cellar, a basement, or a safe room.
A string of tornadoes touches down in Oklahoma. Spinning at 200 miles an hour, an EF5 tornado travels for 65 miles through El Reno, Piedmont, and Guthrie, Oklahoma.
If you're in Piedmont right now, you need to be taking your immediate tornado precautions right now. This is a life and death situation.
Oh, this was the first tornado. This tornado, if you take 8 football fields, put them end to end, that's how wide it was. We had 4 this size. It was absolutely amazing.
It's the 6th EF5 of the year. 3 EF4 tornadoes also develop on this day. But in Oklahoma, only 9 people are killed, compared to more than 160 deaths in Joplin. So what accounts for the difference? Part of the reason is that these tornadoes missed major population centers. But a more important factor may be greater tornado awareness. In the heart of Tornado Alley, the people of Oklahoma are used to living with tornadoes.
Oklahomans are very aware of what's going on in the weather. They stay weather aware. I think most of the audience understands what we're talking about, because a lot of times I'll say we have a big supercell. They know that's a rotating thunderstorm usually, and usually a supercell has that rotation in it. I think they understand them. They love the weather here. Well, you know, if they don't pay attention, they die.
Went to the TV, turned it on. Gary England was on there.
Right now it's along and just north of Interstate 40.
They were tracking the tornado, so I went to the kitchen window and I looked out and I saw it. And that's the first tornado I've ever seen in my life.
I would strongly suggest you take your tornado precautions. This thing has produced a huge tornado.
I went to the safe room and I was in there maybe 30 seconds when it hit.
The low death toll in this state may also be due to the fact that many Oklahomans have a safe room, a reinforced shelter built to withstand an EF5. This one saved 8 lives in Piedmont.
The way that safe room is designed, the structure of it, to tie the structure of the house together is the reason these walls are standing right now.
But a safe room is too costly for everyone to have. So by simulating the effects of tornadoes, scientists at Texas Tech are trying to find cheaper ways to make ordinary structures more robust.
It boils down to cost. We could design a building or a structure that would withstand a tornado. The problem is that most of us couldn't afford to live in that structure. The tornadoes that we simulate in here are based on the mid-EF3 range because about 92 to 94% of all tornadoes fall in that range. The reason why we're doing that is we would like to understand the wind loading on structures such as this scale model of a mobile home. Our preliminary work shows that you have parts of the structure that experience a positive force. In other words, they're trying to push the force in. And then as the tornado gets closer and closer, then you have suddenly parts of the force that is wanting to pull it apart. The other bad part is you have stuff falling down from your roof.
Structural engineers at Texas Tech are also looking at debris impact, trying to replicate the forces of the worst tornadoes, like the EF5 that hit Joplin.
And what we do in this facility is research debris impacts from severe storms. Tornadoes can send all kinds of debris, impaling buildings, livestock, people, cars. It's phenomenal.
Ultimately, we would like to develop codes that say if you live in these tornado-prone areas, you ought to think about reinforcing structures in this way or building a structure in this certain way. That's the ultimate goal.
The devastation of 2011 makes finding ways to prevent future deaths from tornadoes an urgent priority. One important concern is the national radar system. There are 159 fixed Doppler radars across the country, not enough to get full coverage of the lower atmosphere.
Tornadoes form near the ground within the lower several kilometers. One problem that we have is what we call the Earth curvature. So as you move away from the radar, the Earth curves down underneath the beam. And so the problem we have is we're not seeing a lot of the atmosphere near the ground. And that's a huge limitation of the current network.
Jerry Brodsky and his team are working on a solution.
These radars, because they're looking low, they're giving us information in critical areas.
These radar stations are closer to the ground and able to look below the current radar system. They also scan the skies faster. A prototype was put to the test during the 2011 tornado season.
One of the large EF4 tornadoes that occurred here in Newcastle, Oklahoma, was within several miles of one of these radars. That information was sent to emergency managers in the field, rounded everyone up, roughly 1,000 people, and got them in the shelter.
Oklahoma-based meteorologist Kim Klokow is also looking for ways to reduce deaths. She studies how people react to tornado warnings.
The slice of psychology I'm looking at is risk decision science. So people, when they have risky choices, tend to overweight low ranges of probability and underweight high ranges that aren't certain.
Kim is investigating how people affected by the Oklahoma outbreak responded. People like Randy Tucker, hit by an EF4 tornado near Chickasha.
We came out, kind of stood around in disbelief, and then by the time we walked down the road a little ways, then we realized that all of the homes at the end of the road were gone.
Randy survived by running to a neighbor's underground shelter, but with only seconds to spare, despite sirens and warnings on TV and radio.
Some of the most striking things that I'm finding are people aren't necessarily sheltering right away.
Warnings are often ignored because people don't believe a tornado will strike them, especially if they've experienced a false alarm. They wait until they actually see for themselves that a tornado is heading their way. And sometimes that's too late.
After I've collected this data, I'll brief the National Weather Service. We should start thinking about new and creative ways to implement warnings to alert people.
Kim's findings will be used to revise how tornado warnings are issued in the future. But the Holy Grail is still to extend lead time, to give people time to get out of the way. So on the same day that Gary England makes his alarming forecast, Howie Bluestein and his team are back on the road, hoping to catch a tornado forming. They're chasing the big question. Why do some thunderstorms spawn a tornado and others don't? Howie believes the size of raindrops could be a clue, but only now can his new mobile radar measure them. The challenge is to put it in the right place at the right time. And as tornado season draws to a close, this may be Howie's last chance for the year.
Oh, wow. Holy mackerel, we've got 3 hooks. Yeah. We have 3 hook echoes right now, 3 potentially tornadic storms.
The team has managed to place the radar in the path of a storm, picking up hook echoes, which signal the storm is beginning to rotate.
And the southern one is coming fairly close towards us. It's a good thing we stopped.
It looks like it could be evolving into a tornado.
Hope we don't have to move. That's remarkable.
Half an hour later, the tornado is forming, and Howie's radar is recording it all.
This has never been done before, so we will see how the storm evolved on a 2-second time scale. We have a relatively complete look at the evolution of the tornado as it was beginning, as it was intensifying, as it became very strong.
This is the closest anyone has ever come to capturing on high-resolution radar the complete formation of a tornado emerging from a thunderstorm.
I think that's some of the most spectacular tornado genesis I've ever seen, actually.
This new data on raindrops, their size, speed, and direction, might help Howie prove his hypothesis that the size of raindrops could influence why some storms form a tornado and others don't. His new radar reveals something else. A narrow, dry band with no rain or hail. Howie and his team are still trying to determine its impact, but it could be another important clue in tornado genesis. These findings will be integrated into a computer model designed to help forecasters predict deadly tornadoes earlier, increasing lead time and saving lives. As the 2011 tornado season comes to an end, with its extreme devastation, scientists and communities at risk are grappling with further questions. Will destruction at this scale become more frequent?
The reason why tornado disasters are on the upswing is that more people are getting in the way. As our cities expand, the target gets bigger. So tornadoes are more apt to hit major cities now than they were 100 years ago. And that can only increase in the future.
And does global climate change mean it's getting worse?
As the climate warms up and the amount of moisture near the ground increases, that certainly is something which is favorable for producing more thunderstorms.
Probably there's a relationship on the large scale to a warmer climate. We also know that there's a potential for more moisture in a warmer atmosphere, and we are seeing extreme precipitation events occur more frequently due to that.
So could the danger zone expand beyond Tornado Alley?
What we may see, we could see a redistribution of those areas that experience a greater risk from tornadic thunderstorms. We could see that the conditions that favor these outbreaks shift to perhaps the upper Midwest or Great Lakes or Northern Plains over a period of time.
If this really happens, the impact would be enormous, placing more lives at risk from tornadoes and making the quest to understand these terrifying forces of nature ever more urgent.
Debris falling. Oh, it's just in a house! It's just in a house! Oh, stop, stop, stop! Power line's down, power line's down!
Oh my God.
Major funding for NOVA is provided by the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science.
Discovering new knowledge. HHMI.
And the Corporation for Public Broadcasting. And by PBS viewers like you. Thank you.